the slides, they have overlays. So just go step by step.
Yeah, so the first page now. No.
Okay. Okay, start. Share your screen.
When he tells you to flip, then you flip. Okay, so Jose, the first page, you tell us what to do. Go to the next page or stay.
Okay.
Yeah, please. Yeah, you speak.
So first of all, I want to thank the organizers for the kind invitation, and I'm very sorry for the technical problems. My task in this talk is going to be to give a drone view of neutrino physics and the opportunities it brings, both for experiment as well as theory, emphasizing to what extent neutrinos may actually shed light on the fundamental symmetries of nature. Next, please. I start with the current status of neutrino oscillations. You see the upper left two panels show the status of the solar neutrino oscillation parameters and the atmospheric neutrino oscillation parameters. You see that the solar splitting determination is dominated by Kamlan, and now the atmospheric splitting determination is dominated by ice cube instead of super K. Of course, these were the discovery experiments for neutrino oscillation, solar and atmospheric. The discovery has been confirmed in reactor and accelerator-based experiments, which have also provided an improved parameter determination, as you see on the right panels. Next, please. Altogether, we have a very good determination of the two mass splittings, precise determination, and also of two of the three mixing angles. And we have as open issues, first of all, the issue of the neutrino spectrum, normal versus inverted ordering, as illustrated, and the issue of the octant of the atmospheric mixing, and the ambiguous CP determination. Next, please. In fact, zooming on leptonic CP violation and is the target of upcoming experiments such as Dune. And I show here a zoom on the left panel of the current situation, where you can see the status of the atmospheric mixing and the status of the CP phase. I should say this is after the summer conference in Chicago. You see in solid and dashed green the global status of the global oscillation fit, and these are the open issues for the future. We have both the case of inverted ordering in dashed and normal ordering in solid. Just to illustrate, the octet resolution problem, and you see on the right panel that even this futuristic T2HK experiment, we have trouble in resolving the octant if the true value lies. Next, please. Next, please. So much for the oscillation data. I now turn to interpretation, and here the first interesting neutrino oscillation, neutrino mixing pattern is 3B maximal, and it is very simple. It captures the most essential features of the oscillation, namely bimaximal for atmospheric, trimaximal for solar, no reactor mixing, and hence no CP violation. Fortunately, it is relatively easy by exploiting symmetries to obtain systematic generalizations of the basic TBM pattern so as to obtain not only a viable but also predictive two neutrino mixing schemes such as indicated on the right. Next, please. And this translates to this prediction indicated in the green band, which overlaps with the general neutrino oscillation fit over a very narrow region of delta CP, showing the predictivity. Of course, this is just one of a class for the sake of example of the various ways in which one can generalize 3B maximum. Next, please. So now I turn to bilarge lepton mixing, a pattern that we suggested in Valencia, motivated by the observation that the largest quark mixing angle, namely Kabibu, is similar in magnitude to the smallest of the lepton mixing parameters, namely the reactor angle. So the lepton mixing matrix can be separated as a product of two factors. The left one comes from the charge lepton diagonalization. The right piece comes from the neutrino diagonalization. And both of them are expanded as a power series on the small parameter lambda, which is very well measured. So if you know lambda, you know them all. Next, please. This way, one has predictions for the solar mixing parameters indicated in black and the prediction for the atmospheric mixing indicated in blue. And these are very tight predictions given the fact that the reactor mixing is rather well measured. And again, this is one example of a class. I will not bother you with more details. Next, please. Instead, I return to the unitarity test. This is an important one. First of all, if neutrino masses arise from type 1 seesaw, as I will discuss later, you do not expect the neutrino propagation to be described by a unitary matrix. Instead, one has a unitarity violation. The most general way to express this is indicated in red. You just pre-multiply a unitary matrix U by a triangular matrix, the diagonal entries of which are less than 1, and the off diagonals are small but complex. Fortunately, we have already robust bounds on these, on the moduli of these quantities, as indicated in green in this table, but unfortunately, they are still not good enough. Next, please. Fortunately, the short distance physics program at Fermilab is ideally suited to improve upon these alphas. Next, please. And this is not only a luxury, a test, a probe of the seesaw scale, not a very strong one, in fact, but rather it is a necessary step towards a robust CP determination program, for example, at the far detector in Dune, which will be over the next years. So near measurements are absolutely necessary in order to have a long-term robust CP determination program. And this has been discussed in many papers, such as the one of Xiaofeng et al. Next, please. So much for oscillations. Now I move to beta decay endpoint studies as a probe of the absolute neutrino mass scale. As you can see on these plots, this is a heroic effort of the Catherine experiment to to provide the current 90% limit at 1.1 eV, and this should be improved by a factor of 5 in the future. Next, please. If neutrinos are Majorana fermions, there should be also a neutrinoless variety of double beta decays, in which the neutrino emitted by one neutron is reabsorbed thanks to the Majorana propagator. And this is very important. The amplitude is shown here. It provides an independent measure of the absolute neutrino mass scale, and the leptonic weak interaction vertex is sensitive to the Majorana phases of neutrinos. So this is extremely important measurement. Next, please. The resulting amplitude is indicated here in the best parametrization, which is the original symmetrical parametrization we proposed 40 years ago. It's definitely much better than the PDG choice, at least as far as the double beta decay is concerned. And the amplitude M beta beta is expressed depending only on the two Majorana phases, as it must be the case. Now, concerning its dependence on the absolute neutrino mass scale, the lightest neutrino mass scale, this has given in many papers, and I will also discuss it further on. But to start with, I will consider the most favored situation for neutrinoless double beta decay, namely the one that neutrinos are nearly degenerate, as I indicate here on the right-hand plot, which is a different presentation of the M beta beta parameter. It is presented versus this degeneracy parameter eta. So for exactly degenerate neutrinos, eta is equal to 1, and that is the vertical line that you can see at eta equal 1. The current constraint from the neutrinoless double beta decay searches are indicated in brown, the most sensitive of them, namely the one that come from Kamlan-Zen. And on the other hand, cosmology provides an independent limit that comes from the CMB, the most solid one, but also from baryon acoustic oscillations. And altogether, as indicated in this recent Latanzi et al. Paper, cosmology rules out the vertical band, gray band, which is indicated on the plot. Normal and inverted order neutrinos correspond to the two branches that you see, the blue branch on the left and the pink branch on the right. In the case of normal ordering, you can have destructive interference amongst the light neutrinos, leading to a zero cancellation in the amplitude, while this is not possible for inverted ordering. So altogether, the conclusion is that the most favored situation for neutrinoless double beta decay corresponding to nearly degenerate neutrinos is severely disfavored by cosmology. Next, please. The next best bet is the one in which one of the three neutrinos is assumed to be massless. In this case, we have two regions for neutrinoless double beta decay plotted now versus the Majorana phase, because the absolute scale of neutrino mass is 0. You cannot, is very small. You cannot plot in terms of that. So you plot in terms of the Majorana phase. This is an unusual plot, but that's the one that is relevant for this situation, in which one of the neutrinos is massless. By the way, this situation is theoretically interesting. It emerges in several theories. In particular, it emerges in the so-called missing partner seesaw I will discuss later. So if neutrinos are normal ordered, you have now a lower bound on neutrinoless double beta decay, in contrast to the generic situation shown upstairs. Unfortunately, the lower bound lies below detectability, So I move to the inverted ordering case indicated in green. And here what happens is that the lower bound lies substantially higher than the one expected in the generic case. In fact, the lower bound lies within the detectability, and the attainable range of M beta beta is so narrow that one can in fact envisage in the next generation of experiment the possibility of underpinning even the size of the Majorana phase up to this periodicity. Next, please. If all three neutrinos are massive, though, as I indicated in gray in all these three plots, in general, there is no lower bound for neutrinoless double beta decay because there can be a cancellation. And however, more often than not, flavor models of the leptonic weak interaction do imply a lower bound for the amplitude, even when the neutrinos are normal ordered. Unfortunately, you must do one by one. This lower bound is model dependent. Next, please. The most important observation one can make on neutrinoless double beta decay is encoded in the so-called black box theorem. And basically, it states that if you ever discover neutrinoless double beta decay, that will be a real milestone because you can always dress that amplitude, which I indicate here in this big green box. You can always dress it by W boson exchange. After all, the weak interaction is described by gauge theory, so as to produce, in the end of the day, a Majorana mass for neutrino. So at least one of the neutrino must be Majorana if you ever detect neutrinoless double beta decay. So this is a very deep connection, and it is in fact important even for when performing lepton number non-conservation tests at high energy colliders. Next, please. So to wrap up, the standard model provides us with an excellent description of the fundamental interactions, the last brick of which has been the discovery of the Higgs. But unfortunately, the neutrino mass completely misses the issue of neutrino mass. Next, please. The discovery of neutrino oscillation brings neutrinos to the center of particle physics. Next, please. To the extent that addressing the small masses indicated by oscillation experiments in a dynamical way requires us to touch the heart of the electroweak theory. And it may even hold the key to an important issue, namely the stability of the electroweak vacuum. So besides this, neutrinos, as I will show, may also help us in elucidating the architecture of the fundamental theory and its basic symmetries. Next, please. Next, please. Yes. So the basic observation here dates back to 40 years ago and was made by Weinberg. Namely, to the standard model, we can add this unique dimension 5 operator, which turns into a neutrino mass once the electroweak symmetry breaks through the expectation value of phi. And then you are left with a Majorana mass. But that is as far as one can go, just using operator. To proceed further, one needs to have a so-called UV completion of this operator. And here lies the biggest secret of nature, namely identifying what is the UV completion chosen by nature in order to produce the neutrino mass. Next, please. Next, the seesaw provides a very popular way to UV complete the dimension 5 operator, because it opens the way towards a dynamical determination of the small neutrino mass, in which you have not only the V2 VEV that breaks the electroweak symmetry, but also you have expectation values V3 and V1, which must adjust by minimizing the Higgs potential so as to provide no zero neutrino mass. And next, please. The two simplest ways to do this go under the name type 1 and type 2 seesaw. In type 2, the left-handed masses are small because they are induced by the exchange of the heavy right-handed neutrino. In contrast, the type 2 small neutrino masses are induced by an induced triplet expectation value. It is actually anecdotal here that in our old seesaw paper with Schechter, we named these two possibilities the opposite, because we found that the induced triplet VEV was simpler. We called it type 1, and the other one we call type 2. But this is just an anecdote. There was an important difference, next please, between our seesaw and the others, namely that our seesaw was formulated in terms of the standard model 3-to-1 gauge group. And that implies that we can have any number of right-handed neutrino. The number of right and left neutrino need not match, as it is the case in left-right symmetric seesaw. Next, please. So this opens the way to the so-called missing partner seesaw, in which you add, for example, only 2 right neutrinos instead of 3. So you have what Joe and I call the 3,2 seesaw. And this is a missing partner seesaw. One of the left neutrinos cannot pair off with the right neutrino. It remains massless. And this produces the lower bound on M beta beta, which I described earlier. You may even entertain the possibility of adding only 1 right neutrino. It's actually better say 1 singlet and 3 doublet neutrino. And this 3,1 seesaw, missing partner seesaw, has now, it's perfectly okay. It generates the atmospheric scale at 3 level, and it is okay as long as you can generate the other scale, which is smaller, as a loop correction. And this has been recently discussed and named the Scotto seesaw, because that was done in the context where the loop matter. Next, please. You may also consider the opposite situation of having more right neutrinos than left, 2 singlet neutrinos per doublet neutrino, and in the end, you have a 3,6 scenario. This scenario have strictly massless neutrino by just imposing total lepton number conservation. So this leads to 3 Dirac neutrinos added sequentially, so that the 3 light neutrinos are kept massless because they are imposed lepton number conservation. This scenario is the template for low-scale seesaw, and you can generate now finite neutrino masses by assuming this red seed for total lepton number violation in this singlet sector. And the small neutrino mass come from the smallness of this seed, and it is completely natural in the sense of Toft. When you make this seed mass 0, you restore lepton number conservation and massless neutrino, so that's totally natural. Next, please. So this is what is called low-scale seesaw. In fact, there are 2 realizations, the inverse seesaw and the linear seesaw. I'm assuming, for the sake of discussion, the inverse seesaw, because it's simpler. And in this case, you can actually have a double protection, not only the Toft protection, but also a loop protection. Next, please. In the sense that this seed is itself a radiative one, So neutrino mass, the small neutrino mass in such low scale seesaw would be doubly protected. So this is totally natural seesaw as the high scale seesaw. And in contrast to high scale seesaw, it leaves implications for phenomenology. The first one is that neutrino propagation is described by a non-unitary matrix. And the other one is that the mediator of neutrino mass generation is accessible to accelerators. Next one, please. So much for Majorana seesaw. You can also seesaw a la Dirac. This is a more technical thing. There have been many recent papers. I will not bother you with details. I will just give you the bottom line, namely that you can do type 1 seesaw for Dirac. You can do type 2 seesaw. It's just a little more complicated. And small neutrino masses are symmetry protected, very much the same way as Majorana seesaw. And for the time being, we have not detected neutrinoless double beta decay, so this possibility must be taken seriously as an alternative to the Majorana seesaw. And again, you can have high scale and also low scale variations. Next, please. This brings me to flavor a problem. This is the deepest problem in particle physics, and the standard model lacks an organizing principle in terms of which to understand the family replication, why fermions mix the way they do, and why they have the masses which are observed. So this is just something which points towards physics beyond the standard model. Next, please. At this point, I must say that the discovery of neutrino oscillations have left a very important legacy in particle physics. First of all, the discovery of finite neutrino masses. And second, the discovery that leptons mix quite differently from the way quarks do. You see, you have this nearly bi-maximum mixing in the 2-3 sector and a nearly tri-maximum mixing in the 1-2 sector. And this is completely different from the pattern, the CKM pattern that we observe in the quark sector. Next, please. The flavor problem is not only understanding the pattern of fermion mixing, but also understanding this complicated pattern of fermion masses. Here I show the charged fermion masses because neutrinos were already discussed previously. So I do not claim that we have a solution to this problem, but I do claim that we have perhaps the first step, namely, next please, this very simple bottom tau unification formula that I show on the right. It is, first of all, it has nothing to do with SU5. This is just standard model physics supplemented by a family symmetry. And on the other hand, it is a family prediction since it involves quarks and leptons of all three families. And I call this formula the golden quark-lepton mass relation, and it holds very well, as I discuss later. And of course, it's not a complete story. It does not say anything about the top mass, but it is probably a first step towards a complete theory. And it is not a curiosity that appears in one contrived model. It seems to be the common denominator of a whole bunch, a class of theories that have been formulated over the past 20 years. These are UV-complete models. None of them is perfect. None of them is complete, but they all share this golden quark-lepton formula. Next, please. I could proceed to a description of these models, But this is a very arcane subject to this talk, which is the next to last talk of the meeting. Instead of doing that, one by one description of flavor models, I will try to advocate that extra families provide an interesting and perhaps the way to probe the flavor problem. And I will illustrate this in basically two slides. The first one is the possibility of overcoming this ambiguity with respect to the choice of the flavor symmetry. And I will say that in extra-dimensional models with 6 dimensions, you may actually find that the 4-dimensional family symmetry is uniquely determined as the symmetry corresponding to the isometries of the extra-dimensional space. In fact, one may consider a 6-dimensional orbifold compactified on a torus and discover at the end that the unique symmetry, the family symmetry in 4 dimensions is uniquely fixed to be A4, the symmetry of the tetrahedron. And this turns out to be the smallest non-trivial symmetry in terms of which one can stack the 3 families within an irreducible triplet. Next, please. And this choice actually implies our golden quark-lepton mass formula, unificating bottoms and taus. And the predictions of this formula are indicated here in blue, expressed in terms of the least well-measured masses in this relation, namely the down and strange quark masses. So the theory prediction is in blue, and the PDG determination of down and strange quark masses are indicated by the rectangles. So you can see the prediction is very good. Next, please. You also have a prediction, which is very interesting, for CP violation, indicated in the middle panel, and it also implies a prediction on the sign of the CP phase, and a very sharp prediction on the phase. And you see here plotted versus the atmospheric angle. And also the Majorana phase is predicted, and that implies the prediction for neutrino-less double beta decay on the right panel. So this model looks interesting. It also provides a global fit of all the flavor observables, including those in the quark sector. Next, please. Another way to somehow approach the flavor problem in 4 dimensions is warping. And this is the idea of Randau and Sundrum. They use the idea to explain the weak hierarchy problem, even in models without supersymmetry. So what I do here is basically to upgrade their idea and take it as a theory of fermion mass hierarchies. In other words, all the fermion mass hierarchies may eventually be come from geometry. So for my point of view, that is just a fitting, a consistency fitting that we have performed in this example that I described below, in which I also approach the explanation of the mixing angles through the imposition of a family symmetry, in this case T prime, which is a very simple, small symmetry. It's just the double cover of the A4 group again. So this is, however, a non-trivial step, because one must demonstrate that the imposition of a non-trivial family symmetry is indeed consistent with Einstein equations in the work dimension. And we have done that exercise. Next, please. And the conclusion, the prediction we find in this case for lepton mixing is in fact one that already existed before as an ansatz, namely tri-maximum mixing, as indicated here in these 2 equations. They are simple analytical predictions. Next, please. They can be mapped into these predictions for the neutrino-less double beta decay amplitude. It displayed here versus, in the conventional way, versus the lightest neutrino mass. You see the green is the generic prediction. The brown is again the generic prediction, corresponding to normal and inverted ordering respectively. And normal is green, inverted is brown. And this model predicts the blue and red regions, which lie for each case respectively, and both of which lie within the experimental detectability, for example, for the Nexo experiment, and perhaps also for the legend one, if you have inverted ordering. And also neutrino oscillations are predicted, as you see here, a very tight correlation between the modulus of the CP phase and the atmospheric mixing parameter. Next, please. Now I say a word about neutrinos concerning unification. And you have heard many times that supersymmetry provides an attractive way to understand why the strong, weak, and electromagnetic interaction coupling constants merge at high energies. My observation here is that neutrino masses may drive that unification as well. In other words, the physics responsible for neutrino masses may also induce the unification of the gauge coupling constants within a 331 scenario. This is an old extension of the electroweak theory in which SU2 left of Weinberg-Salam is upgraded to SU3 left. This is a model we proposed 40 years ago. And in this context, it is attractive, this context, because we can explain why we have three families. You have three families because that is implied by the anomaly condition, anomaly cancellation condition. And in this case, one may have this neutrino unification scenario even in the absence of supersymmetry. Next, please. This 331 scenario may also harbor an invisible axion solution to the strong CP problem. And this is deeply connected to neutrinos because this Pechequin scale, which I indicated here, in fact, through a Dirac type 1 seesaw. The neutrino mass formula is of course suppressed by the Pechequin scale V sigma, but in order to have a seesaw, I need also a small value of the omega scale. V is the standard electroweak scale. Omega is the scale of the SU3 left. So this model requires physics in the desert that lies between the TeV scale and the Pechequin scale, in order to have a type 1 seesaw suppressed Dirac neutrino mass. And concerning axion detection, we find that the axion coupling to photon is indicated in this right panel by the blue line. And this blue line lies almost an order of magnitude higher than the one predicted by the simplest Dine et al. Axion model. So compared to Dine et al., we have an enhanced coupling of the axion to the photons. Next, please. In here, I try now to fly high, and the idea is motivated by the beauty of neutrinos in SO10. They lie in this expinorio representation. You have the seesaw and everybody. It has, so the idea here is to have a comprehensive unification scenario that includes also the families as part of the unification. And the idea is to unify spinorially. So you take a big spinor in SO18 and you just break it up so as to obtain the family replication. This is a very old idea, very beautiful, but it has been stuck there for 40 years because of a problem of chirality. If you do this, you have mirror families. You don't have the chiral universe we live in. We now suggested 3 years ago in this paper with Frank Wilczek a way to bypass this problem by promoting 4-dimensional Minkowski to 5-dimensional anti-de Sitter and using the orbifold boundary condition to decouple the unwanted mirrors. But we still have a problem. Next, please. Because we have 8 chiral families and we find only 3 in our world. So you have to get rid of 5 unwanted chiral families. And this can be done by observing that they can be bound at low scale because there is an associated non-abelian confining symmetry associated to this hypercolor SO5, which is part of our big orthogonal group. Next, please. And you notice that since you had an SO8, if you use SO5 to confine the unwanted chiral symmetries, the leftover ones may still be arranged with respect to an SO3 family symmetry. And we demonstrated that if in fact this is viable, this is not a complete theory of flavor, but it is viable, and it implies the Pechi-Quinn symmetry, it implies the invisible axiom, and it implies the golden quark-lepton unification formula. So that is one of the reasons we believe that that formula will eventually come to the books in the future. Next, please. This brings me to dark matter. This is the other drawback of the standard model, the fact that it lacks a dark matter candidate. The observation here, made originally by Ernest Ma and now converted into a paradigm in neutrino mass model building, is to postulate that WIMP dark matter is nothing but a mediator of neutrino mass generation through this so-called scotogenic loop. This is a paradigm. There are many models of this type. For example, you can stabilize dark matter by a remnant gate symmetry instead of imposing it by hand, as in the standard SUSY models. You may also have the beautiful possibility that dark matter stability follows from the Diracness of neutrinos. Next, please. This can be realized in many ways, at 1 loop, at 2 loops, with Majorana neutrinos, with Dirac neutrinos, and generically, you are left with a WIMP scotogenic dark matter scenario that you can detect through nuclear recoil in the standard way. Next, please. You may also entertain something which has considered in the last 3 years, is that WIMP dark matter may not be elementary, but rather a composite out of colored states that are scotogenic, and they produce the neutrino mass scotogenically. In this case, you have so-called bound state dark matter, and this is a WIMP dark matter, which is rather WIMP dark matter heavier than about 10 TeV. Next, please. Next, please. This brings me to my conclusion that the neutrino oscillation discovery has left a deep legacy in particle theory. For example, it has brought neutrinos to the center of the stage. It has brought the neutrinos as a way to understand the flavor problem and possibly the strong CP problem, and also that the dark matter can also be deeply related to neutrinos, for example, within the scotogenic scenario. Next, please. And from the experimental point of view, we have a bright future concerning unitarity tests in neutrino oscillation experiments, which are necessary in order to ensure a robust CP violation search program. The search for neutrinoless double beta decay, and the possibility that it may actually determine for the first time the value of this Majorana CP phase, and of course the importance of colliders in probing the mediator of neutrino mass generation. So colliders may have a very rich potential. For example, as we have heard, in the search of displaced vertices associated to the production and decay of the mediators of neutrino mass. Thank you very much, and sorry for the technical problem.
Well, it looks work well. So thank you, Jose, for the wonderful talk. So now we're open for questions. Any questions from online? Some people want to ask. Okay, so locally, any question want to ask?
Hello. Thanks for the nice talk. Just a simple question. So we know the CPU violation fast is always changing. In the beginning, it was like 210. Now it's like close to CPU conserved value. Does it affect to the flavor symmetry models? Thank you.
So which slide you were talking about? They are numbered.
No. I just asking the CPU violation fast fit. I know that is always shifting. Like in the beginning, like 210,
yes.
And right now it's like close to CPU conserved value. How it?
Yeah, well, we have now a very confusing situation. Normal ordering is preferred, and for normal ordering, the preferred value is close to pi. Now, inverted ordering is still allowed at 2 sigma, 2.5 sigma, and if you have inverted ordering, the preferred value is 3 pi over 2. It's close to that. So it is a very confusing situation. It is, we cannot decide. That's why we need Dune and we need future experiments to pin down the exact value of CPU violation. And I actually showed the model that predicts the value and predicts the sign.
Well, okay, so now next question, Martin.
Yeah, hi, Jose. Thanks for the nice talk. So I was wondering, I mean, you showed all those models and I also worked a lot on models. So I like models, of course. But I'm wondering, what do you think is like the important thing a model should cover nowadays? So what is the big challenge for model builders in these days? What do we have to model?
I can say perhaps what I am interested on at the moment. First of all, models that combine a neutrino mass generation with dark matter. And in particular, I think scotogenic models, which are invented by Ernest Ma, are really interesting. And it is there are many possibilities there. Of course, this says nothing about detailed structure of the flavor problem. That's the other big thing, maybe even more important. And concerning the flavor problem, I am quite interested in models with extra dimensions. But we keep trying to combine, for example, even without going that far, we can combine, in fact, we have a recent paper combining scotogenic origin of neutrino mass with, for example, A4 symmetry of the leptonic-weak interaction, and so as to see, to have a combined scenario with predictions also for neutrino mixing, CP violation, and also dark matter. So this, for me, is a very interesting direction, but there are many, many possibilities. In the ambitious point, I would say extra-dimensional models, both of the Randall-Sundrum type, I mean generalizations of Randall-Sundrum, because Randall-Sundrum never talked about fermion mass hierarchy. They only talk about the weak interaction hierarchy. So upgrading their idea into complete theories is interesting because you can combine flavor groups with that approach. But still, determining the fermion masses becomes a geometrical challenge. We as particle phenomenologists, we cannot really do that. And the other possibility is these orbifolds. The orbifolds give you the possibility of actually determining the flavor group, and that is very interesting. So we are now looking at combination of orbifold with dark matter, and we are working on that at the moment. Kaluza-Klein dark matter, also scotogenic dark matter, trying to see. We have, in fact, a paper with Antoniadis doing this, introducing scotogenic in that context.
Okay, so any other question? Jose, maybe I have a more experimental oriented question. So a lot of neutrino experiments is going on. So what is your sort of projection in in the near future? Some results, breakthrough results coming into us. You have some idea?
I don't know. What I can say is that if you look at the CP violation determination we have at the moment after the neutrino conference, it is worse than what we had before. And the reason is that we have this tension between K2K and NOVA long baseline accelerator experiments. They have contradictory CP predictions, and this is why the global result is now worse than what it was before. So I think the first step is to improve upon this situation, and it is a purely experimental question. We cannot really comment.
All right.
In the long, sorry, yes.
Go ahead. So you're done?
Yes.
Yeah.
Please.
All right. Okay. So any other question? Yes. One more question.
Sorry, I think I missed at some point, but I wonder what is the role of the higher dimension to solve the problem that you mentioned?
Well, let me say the following. We have played a lot with many UV complete theories.
Yes, so for example, the strong CP problem.
The strong CP problem.
Yes, I remember that the previous slide that you mentioned about the higher dimension, right?
Can you flash that slide, please?
Huh? Sorry?
Can you show that slide?
Okay.
Which one? Which slide?
Yeah.
The very early one that he mentioned about the higher dimension. Yes.
Already passed that.
Yes.
So here?
Okay, no, sorry. Here I did not mean the strong CP problem. I do not solve the strong CP problem in this model as it is. What I said is that I predict the sign of CP violation. And this is very unique. Most models predict only the modulus. In fact, our next model predicts only the modulus, not the sign. Now, I should also say that this model provides a global fit of all the flavor observables, also of the quark sector. We don't have much prediction in the quark sector, but we fit them, all of them consistently, including the Gatto-Sartori relation for the U and D quark masses. But we have a little tension. I should now say the truth. We predict a unique CP violation in all the theory. So the CP violation of the quark sector is the same as the CP violation here of neutrino oscillations. It comes from the same parameter, and it also shows up in double beta decay. So that's very nice, but we have tension. If you take it, that model strictly, we have, I think, close to 2 sigma tension with the quark sector. We can resolve it very easily by looking at the softer version of the model, keeping all the excellent fit predictions, but releasing the prediction of the CP phase. In this case, the CP phase, the sign is predicted, but the modulus can vary. And then we have no tension. We have an excellent fit, but we don't have this sharp prediction that you see in the middle panel.
Well, okay. Thank you, Jose, for the nice talk. Thanks, Jose, again.
Thank you.
Okay, so we come to the last part of